All right, so we start. It says sketch the magnetic field between two bar magnets placed 4.1 with their south poles facing each other. All right, south pole facing each other. So what do we have? You're going to have your magnetic field pointing towards the south. Why? Because the direction of the magnetic field is always from north to south. North to south. All right. So you're going to have your magnetic field pointing towards the south. So they are entering the south there, right? Then there is space here where there is X. There is space showing repulsion. So the lines are not here because of repulsion, because like poles repel and unlike poles attract, right? So that's for 4.1. So please, when you draw, make sure your lines are not crossing. Right, we move on to 4.2. Two bar magnets placed with opposite poles facing each other. So you've got your north and your south, right? So that's an attraction. So your lines are gonna move from north to south. Your direction of the arrows must be correct from north to south. So that's how you're supposed to have drawn your magnetic field for the two bar magnets with opposite poles and with opposite poles. Right, then number 5. Number 5 says the strength of the magnetic field of the bar magnet is measured at various distances away from its north pole. The results are shown in the graph below. So you're given there your graph, you've got magnetic field strength versus distance from the pole. So that's distance on your x-axis, and you've got magnetic field strength on your y-axis. As you can see, your graph there, it's a hyperbola, right? It's decreasing, all right? It's not a straight line, but it's a curve, all right? So what is happening here? It means as you move away from the poles, your magnetic field strength decreases, right? There's a sharp decrease here. Then here it decreases gradually, right? Then 5.1, does the magnetic field strength change at a constant rate as the distance increases? If not, describe where the magnetic field is, describe where the magnetic field strength changes fastest and where it changes slowest, right? So that's what we have there, right? How do you answer that? Obviously, does the magnetic field change at constant rate? That's not constant because it's a curve. It can only be constant if it is a straight line. Therefore, your gradient becomes constant. But this one, the answer is not, right? So the rate of magnetic field strength versus distance changes fastest when it is measured near to the magnetic pole, right? The slope, that is the gradient of the graph, is steepest at these positions. So here, I think your graph, as you can see, it's steep here. That's why it's steep here, right? Another way to answer this would be, it says, if not, describe where the magnetic field strength changes fastest. So you could use numbers. You can say it changes the fastest between around about, this looks like a 2.5. So you can say between 2 and maybe 8. That's where the graph is a bit steeper. Or you can say 2 and 5. So you can just describe this position here, which denotes the poles. So it could be moving from the poles away from the poles. That's where, when it's closer to the poles, that's where you've got the biggest strength. So as you move away, there's a big drop there, right? So the answer there, it's saying the rate of magnetic field strength versus distance changes fastest when it is measured nearer to the magnetic pole, right? Here I've just given 0 to 5, but you don't have necessarily to put a 0 because at 0 there's nothing here. 0 there's nothing, so you can use any value greater than 0, right? Then when the strength was measured further away, the slope of the graph was very slight. So your magnetic field strength becomes weaker, showing that there's only a gradual change in magnetic field strength at a greater distance from the magnet, which is round about here. You can start from 15 or 10, 10 going that way, right? The values there, they are reducing slowly, right? Which means the distance from the poles is bigger. Right, then next one, 5.2. How would you expect the graph to change if you place the magnet with one which is stronger? Now, so it means, let's say you use a stronger magnet. What effect does it have on the shape of the graph? All right, do you expect it to be steeper, or do you expect it to be after the graph, or do you expect it to broaden here? What do you expect? Right. So on the answer here, this is what you have. For the first one, if a stronger magnet was used, the field strength would be higher at every distance. It would curve up higher at the beginning and remain higher at the end. So your graph is supposed to be higher. It's supposed to be higher here. So if you go to the original graph, how do you see? Let's say at 5. If I'm going to use 5 as my example, all right? If I use a stronger magnet, I expect the magnetic field strength to be bigger than this answer here is about 1.2. So if I plot a graph here at 5, I expect the answer to be bigger. So it should be maybe around about here. And this value here is going to be maybe way above. So my graph is going to be above here. It's going to move here. All right, it will be way above because the magnetic field strength is bigger. So it's going to be above the graph. That's what you're going to have there. Right, my solution here is not exactly showing this. It's showing these two here, assuming this is the original one and this is the other one. But here, when it gets to 0, because it's 0, it will stay like that. But if it's 2 graphs, then it's going to let me just mute everyone here. Okay. So what you're going to have, you've got your magnetic field. Someone is making noise here. Who is this? Okay. Right. So my graph here is not exactly that, and this part is not continuing up until, but the other graph for the strength that is, or stronger magnet, is going to be above. So it will be above the original graph. That's what you get there. Right, then we go to 5.2. 5.2. How would you expect the graph to change if you turned the original magnet around and measure the magnetic field strength from the other pole, right? So your direction for magnetic field changes as well, right? Because we know it's always from north to south. So your graph becomes, the shape becomes like a reflection on the x-axis of the other graph. So that's what you're going to have there, right? So you're going to have the graph starting with negative values coming up like that, simply because of the direction. So because direction is expected from north to south, so it becomes the opposite direction. So you're going to have the other way around. But your graph, the direction will still be the same, but you're moving maybe from left to right. Now you're moving from right to left. Then you're going to have a reflection of the same graph on the x-axis. So this is what you're going to have from the original one. Right. Then we move on to the next one. That was 5.3. The original, let me just read here. The original field strength would be the same value, but the graph would be the reflection about the horizontal axis because the field is directed in the opposite direction. It will be the reflection of the graph about the horizontal axis. So a reflection along the x-axis. Right, that was number 6. We move on to number, that was number 5. We move on to number 6. What happens to the poles of the magnet if it is cut into pieces? All right. Solution, cutting a magnet in half produces 2 smaller magnets, each with a north and a south pole. There are no magnetic monopoles in our universe so far. Right. So when you cut a magnet into 2 pieces, because of the domains in the magnet, you still have your north and your south. So that's the answer there. right? Number 7, what is magnetic north pole? What is magnetic north pole, right? So it's a this is a multiple choice. The position that the north pole of a compass points to. The position that the south pole of the compass points to. The northernmost points on the Earth spin axis. The southernmost point on the Earth spin axis. Remember, wherever the Earth is spinning to give us day and night, that becomes geographic. That becomes geographic. So C and D, those two answers are incorrect because they are talking about geographic north, all right? Because of the spin of the Earth, right? So these two are out. So the possible answer is between A and B. So what is the magnetic north pole? Position that the north pole of the compass points to, all right? Then this one becomes South Pole. So between A and B, the correct answer would be A. So A, the north pole of the compass is the north-seeking pole. It seeks the magnetic north, right? Which is the one that is in the northern direction there. Right, next one, multiple choice. Number 8. One of the yes.
But isn't it what is actually the South Pole seeks the North Pole?
Yeah, but actually,
So
isn't it our magnetic north? Whenever we say magnetic north, remember from the diagram here, let me just see if I can open it here. The one that we say north, magnetic north, actually it's a south, but because we're talking about just magnetic north, right? Where is that one here? Let me just open it. Here it is here. Right. Here we assume there's a bar magnet here, but the one that is up here, we call it the magnetic north pole. So we've got two poles. But actually, when you look at it like as a bar magnet, actually it's a south. But we refer the one that is up here, our magnetic north. Are you answered, Joshua?
okay.
Yes. Actually, it is not inside with the alignment of the metals that are inside. It's not exactly a north, right? We just say north because the compass, that's where it points to. But when we speak about the materials under the ground, that's like a south. And the one that is the south is actually the north, because the north on the compass attracts to the south. So where it is pointing, it can't point to north, and north the repel. So yeah, so here we're not talking about underground, we're just talking superficially here. That becomes our magnetic north pole. Clear?
Yes, sir.
Right, okay. So just be careful with that one, whether the question is talking about on top of the Earth's surface, or what we refer to under, is it referring to the underground? Clear? Right, then we move on to the next one. Number 8, one of the differences between the geographic North Pole and the magnetic North Pole is, one of the differences between geographic North Pole and magnetic North Pole is, we have A, magnetic North Pole always remains in the same position. B, the geographic North Pole always remains in the same position. The magnetic North Pole is found in the southern hemisphere. The geographic North Pole is found in the southern hemisphere. All right. So here, what we have here, we're asking the question is, one of the difference between geographic North Pole and magnetic North Pole is, so if you look at the first one, the magnetic North Pole always remains in the same position. This one, it shifts. There's an article that I saw, I think yesterday when I was going over my phone there. They say the position of the magnetic North Pole has changed. I've saved the link. I'm going to send it for you guys to read. I'll send it on Google Classroom. It was talking about the shift of the magnetic North Pole. I think the other time when we're talking about this, Joshua, you also highlighted something there, right? Right? Okay. Then the next one, the geographic North Pole always remains in the same position, right? This one is true because when the Earth rotates, it rotates on its axis. This one rotates on its axis. So where the position where the Earth rotates always remains the same. It does not change, right? So this is the answer here. Let's just check the C. The magnetic North Pole is found in the southern hemisphere. So when you talk about on the surface of the Earth, magnetic North Pole is above. But when you talk about in terms of minerals under the ground, the north is actually the south. So here we're just talking about on top, right? So it's not in the southern hemisphere, it's in the northern hemisphere. Then the geographic north is found in the southern hemisphere. That's also incorrect. So the correct answer there becomes B. Right, then number 9, explain why the magnetic north pole of the Earth is actually a south pole. Now we talk about what is under the ground now. Right, so here the north pole of a bar magnet seeks the magnetic north pole of the Earth's magnetic field. Since the north pole of a magnet is attracted to the south pole, right, the magnetic north pole of the Earth must be a south pole. So there it is now. When you talk about minerals under the ground which attract the compass, it means actually the north is the south, as per this diagram here, as per this diagram. So for a compass to come to point this way, it means this south should be attracting the north pole on the compass. So actually the south, the one that we say north, actually it is the south. So that's the explanation on that one. The north pole of a bar magnet seeks the magnetic north pole of the Earth's magnetic field. Since the north pole of a magnet is attracted to the south, the magnetic north pole of the Earth must be the north pole. Right, then we move on to number 10. The magnetic field the magnetic field of the Earth shields us from cosmic radiation and from solar wind. How does it manage to do this? So this one is just an explanation. Right. The solution: the magnetic field interacts with electric current that is moving electric charges. The solar wind and the cosmic radiation consist of streams of charged particles. Right, when these charged particles strike living organisms, they damage cells and tissue. Life on Earth would cease if the Earth's magnetic field did not repel these particles away from the Earth, shielding us from the effect. So basically, since the solar winds, they're made up of charges, and the magnetic field, they do interact with charges. So as they approach the Earth, the magnetic field repels them, right? This is also a concept that is used in electricity, where a magnetic field, if it moves where there is a conductor, then current will flow, because a conductor has got electrons, so electrons will be affected by that magnetic field, then they start to move. So same applies here. What is going to happen? The particles that are coming, they are charged, and the magnetic field will repel those, because a magnetic field always repel charged particles. So there could be different ways that you could answer this. All right, this is just maybe one way. There could be different ways of answering it. All right, so that will be question number 10. Any questions? Any questions? Right, before we move on to electrostatics, if we have time, I just wanted us to look at one question paper here quickly. I didn't open it. Let me just see if I can open it quickly. I have one question paper that I just want us to look at. Download it does. Just quickly. Right, this was written last year, 2019, physics. This is what I have. Okay. Let me just open it quickly. All right, it's taking time to open. Where is it? Yeah. Okay, any questions so far while this is opening? Any questions, guys? Yeah, there we go. Any questions? Right, from a past paper, this is what we have here. We just check it with one question here. Okay, there's one here, multiple choice, 1.8. Can you see the questions? Can you see the question that I'm referring to? It says 1.8. Which one of the following materials is a ferromagnetic material? Which one?
Yes, sir, we can see.
Okay. Which one of the following material is a ferromagnetic material? Which one? We've got chromium, we've got carbon, cobalt, and calcium. What would be the answer?
Cobalt.
Come again?
C, sir.
C, cobalt, correct. Right, so cobalt is the ferromagnetic material. So we've got iron, nickel, and cobalt. So chromium is not, carbon is not, and calcium is not. So that's a multiple choice question. All right, let's have a look at another one. Right, this one, number 9. Right, so for number 9, what we have, it says a compass is used to determine the poles of a magnet. The compass is placed in different positions around the magnet, as shown below. The dark arrow indicates the north pole of the compass. So this is north, and the white one is your south. So the dark one, the black one there, the north, is pointing to X. And this one here is also pointing towards X. Right. 9.1, explain the term ferromagnetic materials. What are ferromagnetic materials? The 2 marks. Explain the term ferromagnetic material. How do you explain this? Guys, anyone? Okay, if I just check on our, where is this? Magnetism. Just check on the definitions again. Ferromagnetic material, do I have it here? No. Okay, ferromagnetic material materials that are strongly attracted by a magnet or by a magnetic field. So those are ferromagnetic materials. They are materials that are strongly attracted to a magnet. Those are ferromagnetic materials. Clear? Right, 9.2. It says, is X a north pole or a south pole? What would be the answer?
South Pole. So it's the South Pole.
Come again?
So it's the South Pole.
It's a south pole. Okay,
Yes, sir.
why is it a south pole?
So because new, how will I explain this? So because the dark arrows indicate the North Pole of a compass, so North Pole attracts the South Pole, sir.
Right, correct. So X becomes south pole. That's correct. So if this is north, this cannot be north, okay? Because like poles, they repel one another. So X must be south. Correct. Right, 1 mark. Next one, 9.3. At which position, 1 or 2, will the compass experience the strongest magnetic force? Give a reason for the answer. Where do you get the where do you get the strongest magnetic field force here? Is it 1 or 2? One or 2?
One.
1.
Yes, sir.
Okay, 1. Okay, give a reason. What would be the reason?
Sure, it's closer.
It's closer.
Yes.
Okay. The best reason would be the magnetic force is stronger at the poles, right? Because it's towards the
Oh,
pole here, that's where you get the strongest magnetic force. And it's a bit further from the pole, so the magnetic field becomes less, or magnetic force gets less and less. Okay, we move on to the next one. What is the direction of a magnetic field? Choose from north to south or from south to north. What's the correct one here?
from north to south.
North to south, correct. Okay, we move on to the next one, 9.5. Give one term for each of the following descriptions. Right, 9.5.1. The point in the northern hemisphere where the rotation axis of the earth meets the surface. All right, what's the correct answer here? The point in the northern hemisphere where the rotation axis of the earth meets the surface. What is it? Is it either it's magnetic north or geographic north? Which one? Come on, guys. Which one? Which one? Right? Okay.
So,
Yes.
could you please repeat the question?
The question. Do you see the question here on the? Do you see it? 9.5.1. Can you see it?
Oh yeah.
Yeah, it's 9.5.1. The point in the northern hemisphere where the rotation axis of the earth meets the surface. Right, the answer there becomes geographic north because it's to do with the rotation of the earth. So rotation of the earth is geographic north. So your answer is geographic north. Right, we move on to 9.5.2. The point where the magnetic field lines of the earth enters the earth. The point where the magnetic field lines of the earth enters the earth. What do we call that? It's like we're looking at this one here. The point where the magnetic field lines enters the earth. We're talking about this. We're talking about this point here. This. Where the magnetic fields are entering. So that becomes the pole. Those are the poles there. Where they enter, that's a pole. Right? So we're gonna have, we've got your poles there. Let me just go back to the question. The point where the magnetic field lines of the earth enters the earth, we can call it a magnetic pole. Magnetic pole or a pole, it's fine. Right, next one, state one advantage of the earth's magnetosphere for life on earth. What is one advantage of earth's magnetosphere for life on earth? What's the advantage?
Sir, is it right if I say it protects living organisms on Earth from the sun's solar winds?
Right, that's correct, yes. The magnetosphere protects us from the solar winds or all the whatever is coming from the sun that is charged, that is sent from the sun, right? The magnetosphere protects us from that. Otherwise, we're going to end up having a telecommunication breakdown. We can have, we can be affected by that. So the magnetosphere protects us from this. So these are typical exam questions that you get for magnetism. So you should be able to answer these questions here. Then the next question there becomes your, this is the second part that we are looking at now. So this is the electrostatics. We haven't started with this. That's where we are moving to now. Right, so let's look at electrostatics. We just do an introduction, then we end the lesson. Right, so for electrostatics, it's not the first time that you've been doing this. You've done this in grade 8, 9, right, where you spoke about static electricity, you spoke about like charges, repelling and like charges. So here we're talking about charges. We're talking about plus and minus. In magnetism, we're talking about north and south, right? So please don't confuse electrostatics and magnetism. Here we talk about plus and minus charges, electrons and protons, all right? In the other section on magnetism, we're talking about North Pole and South Pole. So in grade 10, we are looking at two types of charge. We look at charge conservation, all right? We look at charge quantization, and we look at the force exerted by charge on each other, all right? Then we look at polarization, all right? Then in grade 11 and 12, the topic is going to continue. In grade 11, you're going to look at Faraday's law, all right? You're going to look at the right-hand rule, checking how magnetic field is generated around a wire carrying current. Then you've got in grade 12, you're going to look at electrodynamics. You're going to look at how electric motors work, how a generator works, right? All that concept comes from magnetism, right? So here we are creating, we are laying the foundation so that you understand the other concepts later on. Then we move on to the next one. These are the laws that you must just know. We've got principle of conservation of charge. We'll look at it when we look at that. Principle of quantization of charge, we'll talk about that. There are some calculations that you need to know using charge on electrons. Then we've got magnetic field. We've spoken about this one. We said it's a region in space where another magnet or ferromagnetic material experiences a force. That force can be it's a non-contact force. Right, then we've got electric field, a region in space where an electric charge experiences an electric force. So a charged object has got an electric field. A magnetic object will have a magnetic field. Then we have got any object that is mass, it will have a gravitational field. Like the earth has mass. That's why around the earth there is a force of gravity. If you go to the moon has a mass, so it will experience, you'll experience also force of gravity, or you'll have a gravitational field around it. Whose effect, if you are around it, you'll be pulled by that gravity. So an object with a pair of, no, this is also incorrect here. It's any object that is mass, right, is got, it's a region in space where an object that is mass will experience a gravitational force. This one is not right here. This was swapped with the magnetic one. So an object with a pair of opposite poles called north and south, which experience magnetic, this should be magnetic something. It's explaining magnetism because of north and south. It's not gravitational field. Right, then we move on to the next one. Two kinds of charge. There's a swap here. Gravitational field, it's a region in space where mass experiences a gravitational force. So that should be there. All right, so there's a swap here. Two kinds of charge. Two kinds of charge. No, this one is not relevant here. Okay. Then we've got conductor. They're swapped around. Okay, I'll leave these ones here. I'll correct them before I post the handout. I'll correct it. Right. Then we move on to electrostatics. So electrostatics is the study of charges at rest. So we are looking at the positive and the negative charges. And where do these positive and negative charges come from? They come from the protons and the electrons that make up the atoms of the that material that we are talking about. So electrostatics, here it's like a counter argument here to say electrostatics not just a study of charges at rest. In other words, these charges somewhere they move. It is not the study of stationary charges, because the charges they do move. Right? So electrostatics is the study of the imbalance of charge. So that's a better definition to define electrostatics, not just study charges at rest. Because, for example, when you look at lightning, there are charges, and those charges they tend to move. So this definition here is not exactly the perfect one, but it's an imbalance of charges, right? So the forces that charges exert on each other and on neutral objects, all right? Those are alternative way to describe electrostatics. The electric field surrounding charges. So you can also look at the electric field around charges. The interactions that takes place when there's an imbalance of charge. So that's a better way to define electrostatics other than this, all right? So this part here is just trying to give better definitions for electrostatics. So on grade 10, we study two kinds of charge, right? That is your positive and your negative. We also study conservation of electric charge, quantization of charge, the forces that are exerted by the charges, as well as polarization. Right, then electrostatics, we're still talking about that, is about an imbalance of charge within a material. All materials contain both positive and negative charge because they are made up of atoms, all right? And these atoms are made up of protons, which are positively charged, and they're also made up of electrons, which are negatively charged. A charged object has an imbalance of charge. Positive objects have less electrons and protons, right? Negative objects have more electrons than protons, right? So just maybe to explain this, let me see if I can just put the whiteboard here. Okay. So here, for example, if we've got an object, we've got positive, we've got positive, maybe 4. Then we've got electrons, 1, 2, 3, right? So if you look at and then, okay, where's my eraser? Need a pen here. Okay. Right. If you maybe look at okay. If you look at the positive here, the first positive and the negative, they cancel. Then you've got the positive here and the negative, they cancel. All right. So if I can just erase that, that cancels with that. This one cancels with this. This one here cancels with this. So the object becomes positively charged because there's more positive than negative. So a positively charged object is because there's more positive than negative charges, right? So this is just to explain that. Then we have the next one. So the charged object is an imbalance of charge. Positive objects have less electrons than protons, right? So for you to get a positive, there must be more positive than negative. Then you get a positively charged object. A negative becomes the other way around. So you're going to have more negative than positive. Then the next one, the reason why we should not refer to electrostatics as a study of stationary charge or charge at rest is because the effects of the imbalance of charge continue to exist even when charge is moving. So that imbalance even continues and charges are moving. So to say charge that is stationary, that's not 100% true, right? So the best way is to say there's an imbalance of charge. A stationary electron sets up an electric field around it, right? When that electron moves, its electric field moves with it. The effect that the electron has on other charges in its region does not depend on the electron being at rest, right? So that the counter argument about charges at rest, the effect depends on the electron being charged. Electrostatics is study of charges, their forces, their interactions. So we're just explaining again the interaction of charges here. Right. Then how do you make an object to be charged? How do you make or how do you charge an object? All right, so here we have got charge can be separated by friction if a rough surface is rubbed against a smooth surface. So you can create a charged object by rubbing two surfaces. An example would be you take your ruler, then you rub on your jersey or you rub on your hair. Then you try to stick papers or bring it closer to small pieces of paper. Right, by your rubbing, you are creating, the ruler was neutral. So you are now changing you are creating an imbalance of charge on the ruler. So when you bring it to paper that is neutral, those papers are going to be attracted to the ruler, right? So you have created a charge by rubbing, by causing friction, right? So rubbing will generate charge, will generate a charge. When you're rubbing, what happens? Electrons can be transferred from one surface to another by friction. So rubbing on your jersey, electrons are transferred either from the ruler to the jersey or jersey to the ruler, depending which one is gonna is gonna gain the electrons or lose electrons. But friction is not the only way in which charge can be separated. So there are a couple of ways that you can do that. Charge can also be transferred by touching two different neutral insulating materials together and then separating them. All that is required is for the two surfaces to touch each other. This is called triboelectric charging. Right? So there's a triboelectric charge series that shows which ones will gain electrons when you rub two or when two objects come together. Right? I think in the handout I'll also add that list just to share with you what happens when maybe a ruler and a jersey, which one is going to gain electrons, which one is going to lose electrons, because when you rub, electrons are transferred. Right, then the next one, when two different neutral insulating materials touch each other, chemical bonds are formed at the place where they are in contact with each other. If the atoms in surface A tend to hold electrons more tightly than electrons in surface B, electrons will move from surface B to surface A. So it's going back to the bonding, right? The ones with stronger bonds will bind the electrons tightly. The ones that can let go, then those are the ones that will lose electrons, all right? Then this causes an imbalance in electric charge at the two surfaces. When the surfaces are separated from each other, surface A will have more electrons and will be negatively charged. So the one that is going to take the electrons will have more electrons than protons. Therefore, it becomes negatively charged. And the one that loses becomes positive. So it becomes positively charged. This process occurs without friction. So triboelectric charging, it is without friction. That's another way to create charged objects. Charging can also occur through contact. A positively charged perspex rod can transfer charge to a balloon or to another perspex rod. Right? For example, when you go and sometimes you touch the door, you get a shock. It's because there's charge that is being there's charge that is transferred either from the door to you or door to you to the door. Something happens, then you get a shock. So charging can also occur by touching. All right, you touch the door, you get an electrical shock because charge is being transferred then. The positively charged rod steals electrons from the other material, leaving both of the materials positively charged. No friction is involved in this method of charging. Right, then the next one, neutral objects have no charge. Right, all materials contain charge. So neutral objects, not exactly they don't have charge, but the charge balances because all materials have charge. All materials contain atoms. All atoms contain positive and negative charge in the form of protons and electrons. Neutral objects does not mean they don't have charge. What it means, they contain an equal number of protons and electrons. They have no, they've got a imbalance of charge. I'm not sure if this, they have no imbalance. So the charges are balanced actually. So they have no imbalance, they are balanced. So your protons and your electrons are balanced, so they cancel out to make it neutral. Charged objects either have an extra number of electrons, right, and are negatively charged, or they have got less electrons than protons than the. So neutral is same number of protons and electrons. Only electrons are transferred between materials to cause an imbalance, right? So when you look at an atom, what moves is the electrons, not the protons, right? So when an object becomes charged, it is either the electrons have been added or electrons have been removed. Electrons are found outside the nucleus of the atom, so the outermost electrons of the atoms and molecules can be removed from the materials or attached to the materials with relative ease in comparison to removing or adding an extra proton to a nucleus. So it's not the protons that move, it is the electrons. Electrostatic phenomena arise from the transfer of electrons and not protons. Right, then we've got polarization. How are objects polarized? Polarization is the separation of charge in an object that remains neutral. Polarization explains how charged objects attract neutral objects. So basically what we have, if I can just show you on the slide here, this is quite a long one. Let me just check here. Stop sharing. Let me see if I can open. Right, if you can just look at an object that is neutral. That is neutral, you've got plus, minus, plus, minus, plus, minus, plus, minus. Right, so if I bring an object that is positively charged, for example, if I bring an object that is positively charged, what is going to happen? What is going to happen here? This object here is going to attract all the negatives. So all the negatives here, all the negatives are going to come this side. All the four are going to come this one towards the positive, because we know unlike charges attract, and we're going to have all the positives, positive they repel. So positive is going to go to the other side, right? Your positive is going to move on the other side. This is what we call polarization. So you're going to have one side that is negatively charged, and the other side that is got a partial positive charge. This is what we call polarization. The positive are still 4, the negatives are still 4, but because you have brought something that is positive here, it polarizes. So it creates two polar, just like on the earth, you've got your north pole and your south pole. Same applies here. The charges, they become two poles. You've got a negative side that is got negative. You have one side that is negative charges, and you've got one side that is positive charges. So this is what we mean by polarization, right? Today we got extra time from Zoom, but I think I've covered what I wanted to cover. This is just the introduction that we have. Then I'm gonna just do some additions on this handout. Then I'll post this and some few other questions. I'm gonna add the questions on magnetism for you to practice past questions on magnetism. I'm gonna add about 2 questions on magnetism, similar to this one that I've done with you here, right, for you to practice. Then we'll continue with electrostatics in our next lesson. Can we have a next lesson on, when is this? On Wednesday, is that fine?
Yes.
Okay.
Yes, sir.
Any questions so far on what I've explained?
No, sir.
Okay. So I will post all as well. I'll post the the recording. My weekend was a bit hectic. I couldn't post. I'll post it. I will send it maybe to. I'll post it on the WhatsApp group for the benefit of people who couldn't join us. I will post it as well as the other ones that we had last week. I will try to post the video as well as the audio because the video maybe it will take time to download. The file might be big. Maybe I'll send the audio. It could be smaller. Right. Any questions?
No, sir.
Okay. Right. So let's meet on Wednesday. I'll post the work this afternoon. Thank you for joining
Yes,
us.
sir.
Thank you for joining us.
All
Bye,
right.
sir.
Yes,
All
sir.
right. Okay. Enjoy the rest of your afternoon.
Yes, sir.
Okay. Bye.